I'm not actually. You're right now. I'm just saying that if I. Yeah, I'm doing my right dance right now. No, it's unless you really.
I could stay in home.
Real, that's real. My mother. Did that.
Yeah, you're just gonna, and then you're gonna be the next day, now you're gonna come into a bed. I'm so stressed, I have so much homework, I didn't have any time for this.
Like the way.
I feel like you're stuck in my head. You're either just like. Actually, they know it's.
Hi, guys. We have one more new topic to go over before we start our test review. I'm almost done. I'm pretty much finished grading your quizzes. I'll try to enter them in the gradebook tonight. Yeah, I'll try to enter your grades in the gradebook tonight, and if I can't give them back to you tomorrow, I'll definitely give them back to you by Monday. So I'm gonna hope to try to get your quizzes back to you tomorrow, because they're pretty much all graded. We're gonna start, we have one more section to go over, limits at infinity. So today, tomorrow, review, Monday review, Tuesday review, and Wednesday test. Okay. Okay, so page 23, limits at infinity. Let me kind of recap what we've done so far in this unit. The first thing we started with finding limits graphically, right? And we knew that a limit can exist if I can pinpoint 2 points on the graph near our target and see if the arrows are headed in the same direction. If they're both headed towards the same y value, we know there's a limit. If the arrows are not headed towards the same y value, then there is no limit, doesn't exist. And next, we did table of values, right? If you see a bunch of decimals and those decimals are leading you, the y value decimals are leading you towards a specific y value. Let's say it was like 8.5 to 8.6 to 8.7 to 8.9. And then from the other side, it's 9.2, 9.1, 9.01. You know that that's giving you an indication that the y value is headed towards 9. So that's the limit. But most of our work was algebraically, right? Algebraically, if the x is approaching a real number, we went through, our first step is always plug in that whole number, right? We don't want to get distracted with anything with decimals because we haven't arrived to that point yet. We always plug in the whole number, whatever the x value is, and just insert into the expression, because we have 3 categories that we have to kind of put ourselves into before we go too far into each category, right? So either if you get a real number, you stop. That's the limit. There's nothing more to do. No decimals involved at all. Okay, even if it's a one-sided limit. If you insert your expression into your x value into your expression, and if you get 0 over 0, you know that there's a hole. The limit exists. No decimals involved. One-sided limit doesn't play a role. But we have 3. This is what the last quiz was about, right? There were 3 ways to go through cleaning up. Either you factor, right, or complex fractions. You got to do common denominators or constant method with radicals, right? And you knew that as soon as you saw 0 over 0, you knew that there was a real number waiting for you at the end. You just have to algebraically get to that answer. But again, nothing to do with decimals, right? We don't do anything with decimals if it's a real number or if it's 0 over 0. Now, final scenario is if it's 10 over 0 or 8 over 0, then you know that there's a vertical asymptote and that the limit does not exist. Only when the limit does not exist do you consider to do something additional if there is a call for a one-sided limit. Then you involve decimals, because that's the only time that you care about, oh, I'm choosing between positive or negative infinity, because my graph is either headed up towards positive infinity or negative infinity, because there's this wall, there's that vertical asymptote that this graph is headed towards. That's the only time you use decimals, okay? And in the past, students have tried to force decimals into other scenarios, and it's never gonna give you the right answer, okay? So we have to be disciplined and only use decimals when a very specific situation comes up, okay? If there's a vertical asymptote, okay? And if there's a one-side limit. Any other time, we don't do anything with decimals. We just take care of the whole number, and that's it. All right, so we have one more thing to do with limits, and this is limits at infinity. Okay, so I want to just kind of draw this out real quick. You can find some space on your paper or not. You can just look what I'm doing here. So we know what this looks like. Okay, limit as x approaches to f of x equals positive infinity. Okay, so this means that there is a vertical asymptote. Okay, because as I approach 2, my y value, right, both sides are headed towards positive infinity. We know this is a category under does not exist, and this is an indication that there is a vertical asymptote. So this is an indication that there's a vertical asymptote happening at that point. Okay. Now the reason why I want to bring this up is because today our limit statement is going to look a little different. It's going to look more like this. Okay. Notice this looks similar because there's 2 and infinity involved, but this is very different. This is saying we're not approaching a real number. We're extending past our view in our coordinate plane. This is saying that as the graph exits from view, it's going to flatten out, and it's going to flatten out towards 2. And this is an indication that there is a horizontal asymptote occurring. So I put these next to each other because I want us to see the distinction. Okay, one is telling us there's a vertical asymptote. The other is telling us that there's a horizontal asymptote. But they look kind of similar, but the x's and y's are different. So today we're going to be exploring horizontal asymptotes. Okay. All right, so let's go to our notes. Now, when you see a limit problem, and if the limit is approaching infinity, we're going to have to switch gears. We have a completely different set of rules for infinity. If it's a real number, we just plug that real number in, right? Well, we plug that whole value in, and we go from there. But if we see infinity, we have to separate ourselves and consider that this is a completely new set of steps to consider. So if it's approaching infinity or negative infinity, we compare degrees between numerator and denominator. Maybe you've done this before when you're talking about horizontal asymptotes. So if we're doing limit as x approaches infinity, we're talking about horizontal asymptotes. And algebraically, we're going to be comparing the degrees. So let me go through the scenarios here. If your numerator degree is less than your denominator degree, then the horizontal asymptote is y equals 0. Or in other words, your limit as x approaches infinity or negative infinity of f of x is equal to 0. And limit as x approaches infinity and horizontal asymptote, a lot of times they're interchangeable. So we're going to go back and forth between those two statements. So let's look at an example here. Okay. Limit as x approaches infinity. So we look at that infinity, we realize, okay, we're not going to plug numbers in. We're going to go directly to our steps, which is looking for the highest and lowest, sorry, the highest degree in the numerator, and also picking out the highest degree in the denominator. Okay, what's the degree in the numerator? 2. What's the degree in the denominator? 3. The denominator has a higher degree, okay, and that means our limit is going to be 0. And that also means that our horizontal asymptote is going to be located at y equals 0. Okay. If you want to memorize it, that's fine, but I also want to kind of help us reason this out. You know, why is it equal to 0? So you look at the powers here, x cubed versus x squared, which is growing at a faster rate, denominator or numerator? Denominator. So if the denominator is getting larger faster than the numerator, that means that gap is widening. And if the denominator is growing faster than the numerator, what's happening to that fraction? Smaller,
Smaller.
smaller, and smaller. If it's going to infinity, that gap is going to get smaller, smaller, smaller until it gets to 0. So if your denominator is higher, right? If you think about a fraction where your denominator is really, really large, that fraction is smaller and smaller and smaller. Okay, second scenario. If the denominator degree is equal to the numerator degree, then they're basically moving at the same rate. And that ratio is going to tell us the rate that they're moving in, or where that asymptote is going to be. Okay. So if we look at example 2 here, infinity, we know we got to compare degrees. That infinity is telling us to do that. So what's the degree of the numerator? 2. Denominator is also 2. Now, they may not always be in order, okay? If something is out of order, you got to look at every term and find that highest exponent. Degrees are the same. That means they're both growing at the same rate. And then they're growing at a rate that is relative to that ratio. So it's just going to be equal to 5/2. Which means that our horizontal asymptote is also y equals 5/2. Now, let me do one more instance of this, and this tends to give some students trouble, and I wanted to kind of see it so that we can process it and then not make the mistake on the test or quiz. Okay, so I wrote here, limit as x approaches negative infinity, 2x squared minus 3 all over 4 minus 9x squared. All right, so we see infinity. We know we got to go through our process comparing degrees. Numerator has a degree of 2. Denominator has a degree of 2 as well. So we find the ratio, which is what? 2 over negative 9, okay? Do we need to make any adjustments here? So the answer is just negative 2/9, okay? We don't change the sign of that. And why do you think this problem kind of makes students pause or, consider that they may have missed something?
They need to fix the negatives.
Right, so I think that's the issue. So they see that negative infinity and they feel like, oh, I gotta do something with that negative infinity, so I'm gonna change the sign to indicate that I took care of it. Your horizontal asymptote is gonna be the same whether you stretch towards positive or negative infinity. If the degrees are the same, you just take the ratio. Don't let that negative infinity throw you off. Okay. We don't do anything with that negative infinity. It's going to be the same asymptote, whether we're going to the left or to the right. Okay, so don't change the sign just because you see that negative infinity there. Put a star next to that. I see some students make mistakes in the past. Okay, third scenario. If the numerator degree is greater than the denominator degree, then horizontal asymptote does not exist, which means that the limit is either positive infinity or negative infinity, right? The graph is not going to flatten out. It's either rising up without bound or it's going down without bound. Okay, so we see infinity here. We know we got to compare degrees. Numerator degree is 3, denominator is 2. So let's think about this for a moment. The numerator is growing at a faster rate than the denominator. What's happening to this fraction? Getting larger and larger and larger, right? And it's either growing larger towards positive infinity, depending on the sign, or it's going down to negative infinity, depending on the sign. Right? But we know it's going to go without bound. It's never going to flatten out at any point in time. So this is kind of similar to what we did with the previous vertical asymptotes, where we got to check between two options, because right now we have two options that we got to deal with. But we're not going to deal with decimals. We're going to head in the direction. We're going to choose a value to plug in, that is in the direction that we're headed towards. So infinity, that's a large number. So let's choose a large number that kind of represents where it's headed. So you're either going to test positive 100 or negative 100. That's, to me, that's an easy large number to involve ourselves with, depending on whether it's approaching positive or negative. So here, the positive and negative does make impact. It doesn't if the degrees are the same. It doesn't if the degree is higher in the denominator. But it does make an impact if the degree is higher in the numerator. So here, what's an appropriate number for us to test? Test x equals positive 100. Yeah, we're headed to the right, so let's choose a number to the right on our number line. So we don't care about what the value is. Just like before, we can easily do this without a calculator because we can just reason in our heads whether our numerator will be positive or negative. So if I plug 100 into the numerator, what do we get? Positive. Denominator, also positive. So positive over positive is positive. So positive infinity. We know that the graph is headed up and it's going to continue to go up as it exits from view. Okay. Any questions as you look at this, right? Completely different set of rules, but it's not too bad, right? We just have to make sure that we don't get thrown off here and that we remember to test if the degree is higher in the numerator than denominator. Okay. There are some other scenarios that I haven't gone over in terms of how to deal with those, but maybe I'll get to that tomorrow. But let's go down to the bottom and see if we can work through these problems and reason through them using the above as examples to look at. Okay, so I'm going to walk us through 4 through 6, and then you guys will try 7 through 9. But if you're good with this, then you can just go at your own pace. Okay, so number 4, limit as x approaches infinity. Okay, so infinity we know. Okay, separate category. We don't plug in a number. We go directly to the degrees. Numerator and denominator, which has the higher degree? Numerator, which means that there is no limit, but we can say it's going to go in one of these two directions. Okay, so we're choosing between these two options. What can we do to narrow down the choice? Let's test a large number, right? What can we test? Positive 100, because we're headed towards positive 100. We're moving to the right. Okay, so 100 in for x. I don't even have to write this out. Numerator is positive or negative. Denominator, positive. So okay, number 5. Approaching infinity. Compare degrees, right? Again, numerator is higher. We have 2 options. Now we test negative 100 because we're going in the opposite direction, right? Let's choose a number in the direction that we're headed towards. Insert negative 100 in for x. Numerator, what do we get? Positive. Denominator, we get negative. Yeah, negative 100 times 2, that's a large negative number. Minus 5 is still negative. So negative infinity. We see infinity, we compare degrees. What do you notice? Degrees are the same. So we just focus on our ratio, which is negative 0.2, right? We got 3 over negative 2, which is same thing as negative 0.2. Do we need to make any adjustment because of negative infinity? No. Leave that alone. Don't let that negative infinity throw you off. You're not going to change anything, just the ratio. Okay, so try 7 through 9, and then I will go through them. Number 7, approaching infinity. Compare degrees, they're the same. We look at the attached coefficient in front, 3 over -2, and that's it, right? Nothing, we don't want to do anything. Once we know it's a ratio, we just take the ratio. We don't let anything throw us off. Number 8, degree is higher in the denominator. If the denominator is growing faster than the numerator, that fraction is getting smaller, smaller, smaller. Limit is 0. Number 9, degree is approaching infinity. We compare degrees. Degree is higher in the numerator. We have 2 options. We're either headed towards positive or infinity. We want to go in the direction that we're headed towards, so we can test negative 100. Numerator is negative. Denominator is positive. Negative infinity. Any questions there? Okay, so I have 2 minor topics to go over on page 24, and then we'll circle back and do a random assortment of problems. Okay, I think this is, and the real test is going to come in when everything is mixed together, and we want to know, can we keep everything straight in our heads, right? When everything is mixed. So let's go to page 24. Okay, I call these minor topics because page 24, this type of problem doesn't show up very often on the AP exam, but it has shown up. So that's why we want to go over it. I just got done saying that if there's a ratio, if there's a horizontal asymptote, it's never going to be different on either side. And here's an exception to the rule. This is a strange looking graph. This is not a rational function. This is one where there's a radical in the denominator. And this graph is going to, as you can see, it produces a graph that, depending on the direction, we have different asymptotes, right? One is flattening out at one y value, and the other is flattening out at a different y value. But you see that the graph looks a little strange, right? So there's a certain thing about this that makes it have that property. So if there is a radical in the denominator, the way we find horizontal asymptotes is we got to test the limit in both directions. Because that square root is doing something to force a change in sign. So let's look at this one at a time and talk about what's different about this. Okay, so let's start at the beginning. We see infinity. We know we got to compare degrees. So what's the degree of the numerator? 1. Okay, numerator is degree 1. Denominator, okay, can be a little tricky here. What is the degree of the denominator? It looks like a 2, but it's actually what? 1. Why is it 1? Yeah, that square root is going to take away that x squared, and it's going to get it down to degree 1. So do the degrees match? Yes. So we got to take the ratio of the coefficient. So the coefficient for the top is 3. What's the ratio in the denominator?
4. No, 2.
Good. It's the square root of 4. So a couple of things that's going on here, right? So square root of 4 is 2. So therefore, the limit is 3/2 as it heads to the right, which means that there's a horizontal asymptote at y equals 3/2. And that is what this graph is showing. This is demonstrating visually what we found. Okay, so a couple of tricky things here, right? We got to understand the square root is going to make an impact with the degree, and it's also making an impact on the coefficient. Okay. So there's one asymptote. Let's find the other one. So limit as x approaches negative infinity. Okay. Same function. Infinity, we see the degrees match. And so it's still 3 over square root of 4, but this is headed towards negative infinity, which means that it's going to be accumulation of all these different negative y values. And if you can imagine the negative y value impacting the numerator and changing the numerator to a negative, but is this negative going to have any impact on the denominator?
No.
It's not. It's going to stay positive, right? So that's why there's this sudden change in sign. That is why we get a negative 3/2. Okay. This negative infinity is causing a different sign out of the numerator, but not out of the denominator. And so all of a sudden there's this shift. And so there's a horizontal asymptote at y equals negative 3/2. So the big picture here is this. Whenever you see a radical in the denominator, you take the ratio of the coefficient after, whether it's 3, making sure that you're involving the radical. But there's always going to be a negative version of that ratio for going to the other side. It's always going to come in pairs. It's always going to be a positive version of the ratio and a negative version of the ratio, because this radical is going to force a non-change in sign, whereas the non-radical is going to suddenly change signs, and that's going to, that imbalance is going to cause a different sign. Okay, so that also means that if this limit was a negative value, then this limit will have to be a what? A positive, right? So just know that they'll come in pairs. It's a plus and minus of the same ratio. 2 split asymptote. This is only going to happen with this type of problem, though. Any other problem, rational functions doesn't have this behavior. It's all same asymptote on either side. We're not going to have 2. So it's a very specific type of problem, but it's an AP topic, so we just want to quickly go over it. Okay, make sure we've got that covered. Yes.
Wait, could you explain why the bottom one's negative?
Right, why the bottom one is negative. Okay, so imagine I plug in a negative 100 or negative 200 or negative 300 versus a positive 100, a positive 200, a positive 300. If I plug in a positive number, you see how the numerator is positive and the denominator is also positive? But if I plug in a negative number, the numerator is going to turn into a negative.
Oh, it's not squared.
Right, but then here, this is, square root, but it's also being squared. So this negative is not going to have any impact below, and that's going to cause a shift in sign, and that's going to cause that to be a different sign.
Okay.
Yeah. Okay, bottom of the page. All right, this is called comparative growth rates. This is a very specific scenario, but it can be helpful, especially when we move in later on. We're going to be talking about curve sketching, and it's just nice to know these properties to help us gather information quickly in terms of end behavior. So this says families of functions grow at predictable rates in relation to each other as x approaches infinity. So that's important. This special relationship does not apply if we're going towards negative infinity. Something like this. No relationship if x is approaching negative infinity. So comparative growth rates really only works if we're moving to the right. So let's compare the different families of functions that shows up a lot in our course. The first is logarithms. Okay, so logarithms, natural log, anything that's involving logs, grows at the slowest rate. Okay, so as it moves to the right, you can see it's increasing. initially it increases at a fast rate, but it's going to settle and it almost looks like it's going to flatten out, but it's just going to rise very, very, very slowly. So an example of that, natural log of x, is out of the ones that we use a lot, is the one that grows at the slowest rate. Followed by radicals. The radicals has a similar shape to natural log, but it rises at a faster rate. Polynomial or algebraic, anything that is greater than degree 1, we can see that it's growing at a much faster rate, right? So it's able to reach a higher y value without waiting as long as natural log of square root of x. So an example could be x squared, also could be like 3x minus 2. So anything that's algebraic, those are all in that category. And finally, we got exponential functions. These are the ones that grows the fastest in terms amongst the ones that we use. So exponential functions are ones where the variable is in the exponent. So e to the x, 2 to the x, 5 to the x. These are all examples of exponential functions. Okay. Okay, so here is the general rule. Okay. First, limit has to approach infinity. And we can't have any mixes of families. If it was like natural log and radical, the numerator, and the bottom with polynomial and exponential, that's too complicated. Okay, we're not going to be able to get a quick read on as to what the limit is. But generally, if it's just one clean function over another type of function, the idea is that if my slower function is up top and my faster function is below, what do you think that limit is going to end up being? Is that fraction getting larger or smaller?
Smaller.
Smaller, which means that it'll approach 0. Okay, so that's nice. If I can pair them up and see that relationship, and if I realize that my family function is growing slower above and the family function is growing faster below, then it's a quick limit problem. It's just going to be equal to 0. Okay. Now let's say the faster function is above, and the slower is below. Is there going to be a limit? No. So this means this fraction is getting larger and larger and larger, and it's going to be heading towards either what?
Positive or negative infinity.
Positive or negative infinity. And just like with previous limit problems with horizontal asymptote, we're going to test a large positive number. Okay. We're never going to test negative 100 because this doesn't work towards the infinity. So we're only going to test 100, and then from there we can decide between positive or negative infinity. So it's meant to be helpful because we want to be able to, something that looks complicated. If I can put the functions into these proper slots, then we can quickly say, oh, that's easy. That's either 0 or positive or negative infinity. And so that can kind of speed up the process for future problems. But again, it is very specific, right? It's not going to work for every scenario. But let's just see if we can practice through these comparative growth rate problems. Okay, so first, limit as x approaches infinity. That's good. We know we can potentially do this, if only if it's headed to the right. So let's see if we can categorize these families of functions because they are specific, right? They're not mixed, and we can definitely tell which family they belong in. Okay, so the numerator is part of which family? Radical. It's a radical. Denominator is algebraic, polynomial. You can write either one. Which one is growing at a faster rate?
Polynomial.
Which means that the limit is
0.
0. Yeah. So something that looks complicated, we can quickly find the conclusion for that limit simply by relying on looking at the families of functions. Okay, let's do 13 first, and then we'll go down to 12 and 14. 13. Again, limits approaching infinity. All right, numerator is what? What type of function is it? It's log. Denominator is polynomial or algebraic. Okay, which is growing at a faster rate? The bottom one, so limit is still 0. Okay, limit approaching infinity, it's good. We know we can go through this growth rate here. Numerator, which family of function, which family does that belong to? Exponential, because the variable is in the exponent. Okay, variable in the exponent means exponential. Denominator is polynomial. Which side is growing faster? Between what? All right, there is no limit. The limit, that means the graph is either headed towards positive or negative infinity. There's no asymptote. And how do we decide between these two? Test 100. If I insert 100 in for the numerator, what do I get?
A negative.
Negative, because that negative is going to stay. Denominator will be
Positive.
positive. So negative over a positive is
Negative.
negative. Okay. Number 14, x approaching infinity. Okay. Let's see if we can classify this, each of the sides here. So numerator is radical. Denominator is logs. Which side is growing faster?
Radical.
Good, radical. So not going to be a limit, but we have two choices to decide between. And we'll test 100 again. Numerator is
Negative.
negative. Denominator is
Positive.
positive. Okay, any questions there? Okay, let's go back and do a few of the problems that we skipped over. Page 16. Back to real numbers here, page 16. Okay, I want you to try 7 through 10. Page 16. So, okay, now we got to reorient ourselves, right? We don't compare degrees here. These are real numbers. So let's go through this process real quick. What's the first thing that we do? Plug in.
-3.
It's just the whole number, right? Don't even think about decimals unless you realize it's a vertical asymptote. Then you can go back and think about it. But and if you don't come across vertical asymptote, it's not going to play a role at all throughout the problem. You're never going to touch decimals for the entirety of the problem. Okay, go through that. I'll go through the steps after you guys had a chance to try it. So you guys get 0 over 0. Yes, there's a hole. We got to go through factoring, reduce, but no decimals, right? At all. Multiplies to be -18, adds up to be 3. Reduce, if possible. X plus 3. I can undo that fraction, bring that denominator up. Reevaluate just the whole number, right? Just the whole number. So this is virtually the same problem that you would see on your previous quiz. It's just that there's that one-sided limit notation, but it's not going to play a role at all for this problem. Okay, number 8. Plug in -4 first. And what does that tell us? 31 over 0. Vertical asymptote, which means that the limit,
Does not exist.
right, limit doesn't exist. Now we can go back and ask, do we need to do anything more beyond this? Yes, right. Now we know that, okay, the full limit doesn't exist, but it's not asking for the full limit. It's just asking, how is the graph moving? Is it going up to positive or down to negative infinity? So we know we have 2 options to choose from. Now we can play with decimals, right? Only in this very specific scenarios are you going to be dealing anything with decimals. Got to choose a value slightly to the right of -4. So what's a good number to test?
3.9.
Negative 3.9. Yep. Slightly to the right of -4. Okay. Okay, so numerator, pretty easy to spot. That's going to be a positive value. Now the denominator, maybe you don't know what -3.9 is squared, but you know 4 squared is 16. So 3.9 squared is going to be what? A little bit less than 16. So number less than 16 minus 16 will be negative. Okay. Yeah, you guys have homework tonight over 3.5. We'll finish up 9 and 10 tomorrow, and then we'll do a full overview, and I have a test review packet for us to start working on tomorrow. Okay. Okay, don't forget your phones. Only to get 10 more. 0 or real number, cross it out. Right? One time.
At the hiccups happen. Yeah.
So whenever I see this, I like, if it helps, you kind of break it into your parts. The left to the right. That's okay.
Oh, that is really good. I don't like them. I never like.
This is easier to look at, right? Oh, that's right.
You bring that to her and be
So,
like.
you gotta set this on any condition. F of A.
I didn't understand that.
That's right.
Oh, Oh, my.
Limit involves connected part of the limit. This is not, this is the point. We don't use this. We use these. Alright, so we need to do one side limit. Let's take, let's do one limit. We don't need to do two things. First things first.
It's gonna rain. Not true.
It changed.
So now there's a hole. Keep going, right? There's a limit waiting for us.
I
Factor.
disagree. I'm so disappointed, honestly. It rained like all night last night. I don't think I
Well, that is the, it's not self for A, but if you keep going, right? It's been through half the thing. So what's the third thing? Third condition is asking, does the second equals equal to C? You want it to be seven. Because I need to find, paragraphs that actually use something like this. This one is less than A, it's greater than that, only this one. If I plug in the function, there's no variables. So it's gonna stay.
I wasn't speaking.